So now we are going to discuss about properties and utilization of common polysaccharides, including starch, cellulose, glycogen, hemicellulose, and pectin. Polysaccharides are carbohydrates containing more than 10 monosaccharide units. When polysaccharides is hydrolyzed, it will yield 100 or even thousands of monosaccharide units, whatever is being contained by that particular polysaccharides. Polysaccharides commonly present in foods include starch, cellulose, glycogen, hemicellulose, pectic substances, and gums. First of all, we will discuss about starch, which occurs widely in vegetable kingdom. More than 80% of all food crops are composed of cereals and starchy food crops. This starch is natural polymer of D-glucose. A very high proportion of world's food energy intake is being provided by starch only. It occurs in nature as microscopically small spherical particles or granules whose size and shape are characteristic for each species. This starch is formed in plants by condensation of a large number of glucose molecules into two types of polymers, that is amylose and amylopectin. As you know, amylose is a linear polymer which may contain more than 2000 glucose units. Each glucose unit is attached to another glucose unit via alpha-1,4-glycosidic linkage, whereas amylopectin is highly branched polymer. In each branch, there are 20 to 30 glucose units, and each molecule contains several hundreds of these branches. Glucose units in linear branch, even in amylopectin, is attached with alpha-1,4-glycosidic linkage, whereas branch points are attached with alpha-1,6-glycosidic linkage. Both amylose and amylopectin molecules are deposited in starch granules in an orderly radial pattern. There are various sources of starch. Specifically, this is divided into two groups, that is cereals and millets and roots and tubers. Cereals and millets contain in the range of 65 to 85% of starch. For example, rice, wheat, maize, etc. Whereas roots and tubers contain in the range of 19 to 35% of starch. For example, in tapioca and potato. What is the basic difference in both of these groups? Let us see. Cereal starch paste containing 5% of solution on cooling sets into a thick jelly, whereas tuber starch paste of 5% concentration remains simply as a fluid and does not set to a thick jelly. Cereals which have low moisture content, starch granules are embedded in a hard proteinaceous matrix in cereals, which requires preliminary softening in case of starch extraction, whereas potato contains high moisture content, and because of that, no preliminary softening is required for starch extraction from potato. Now let us see about amylose. Amylose is long unbranched chain of D-glucose containing 500 to 5000 glucose molecules linked via alpha-1,4 linkage. Its molecular weight is approximately 105 to 106 Daltons. Retrogradation is a process in which dilute solution of amylose on keeping turns turbid due to the precipitation of the amylose. It is one of the important characteristics of amylose. Amylose is responsible for stiffening of cooked rice on standing and it gives blue color when reacted with iodine. Amylose content of a starch vary depending upon botanical species of that particular starch. Cereal starches such as wheat starch contains 25 to 30% of amylose, whereas corn starch, also known as amylomase, contains 40 to 80% of amylose. But waxy maize doesn't contain even a fraction of starch. Here you can see the structure of amylose, where glucose units have been linked via alpha 1,4 glycosidic linkage. Each glucose unit is joined through that linkage only, alpha 1,4 linkage. Now, a second component of starch, that is amylopectin, which is branch chain polysaccharide component of starch, and these chains are linked with alpha 1,4 as well as alpha 1,6 linkage at branching points. Its molecular weight is 107 to 108 Daltons. One molecule of amylopectin may contain 50,000 to 5 lakh molecules of D-glucose, and it gives purple color when react with iodine. This is structure of amylopectin. You can see here straight chain of amylopectin is linked via alpha 1,4 glycosidic linkage, whereas at branching point there is alpha 1,6 glycosidic linkage. Now, gelatinization of starch, which is one of the important character of starch. This is process which breaks down the intermolecular bonds of starch molecules in presence of water and heat, allowing the hydrogen bonding sites to engage more water. This is a process in which irreversibly dissolves the starch granules. Penetration of water increase randomness in the general granule structure and reduce number and size of crystalline regions. This crystalline region is responsible for entry of water into the molecule. As during gelatinization, there is reduction in number and size of crystalline regions. There will be restricted entry of water. During gelatinization, heat causes such regions to become diffused in the chains, and the chain begins to separate into an amorphous form. Gelatinization is influenced by a number of factors, including plant type, size of the starch granule, amount of water present, pH, gelatinization of temperature, and the length of the heating. Some type of unmodified native starch starts swelling at 55 degrees centigrade, whereas other types of starches start swelling even at 85 degrees centigrade. Next important characteristic of starch is retrogradation. This is the process of dissolved starch becoming less soluble. Retrogradation of cooked starch involves amylose and amylopectin. Amylose undergo retrogradation at a much more rapid rate than does amylopectin. Rate of retrogradation depends on various factors, including botanical source of starch, molecular ratio of amylose and molecular ratio of amylose to amylopectin, starch concentration, temperature, salts, and surfactants. Bread stilling is one of the important example of starch retrogradation, which takes place due to the gradual transition of amorphous starch to a partially crystalline retrograded state. Now, modified starches. Behavior of pastes of common native starch used in most of the food industry is often unsatisfactory. Modified starches and starch derivatives with more sophisticated stability characteristics have been developed to meet different purposes to produce varieties of food products. Modified starches include acid modified starch, pre-gelatinized starch, cross-linked starches, ester and others of esters and ethers of starch, starch phosphates, and hydroxyalkyl substituted starch. Hmm. For preparation of acid modified starch, starch granules are heated with dilute hydrochloric acid to a temperature lower than the gelatinization temperature. During this acid modified starch preparation, granules swell less during gelatinization, which is resulting in reduced volume and lower maximum hot paste viscosity. Even its solubility in hot water is increased, the extent depending on degree of acid treatment. This acid modified starch is being used mostly for preparation of fruit gums. Strength and clarity of the resultant because strength and clarity of the resultant gel is improved comparatively, and that acid modified starch is being used for preparation of fruit gums. In this acid modified starch, viscosity of gel is reduced, and because of that, hot gel can be easily poured into molds. Even gel strength has been found to be increased because of degradation of amylopectin, whereas gel clarity is improved, which is demanded for production of fruit gums. Next modified starch includes pre-gelatinized starches. It is prepared by destroying the granular structure on cooking, having considerable reduction in paste viscosity. Here, cooked paste is then dried on rollers or in the spray dryer. This powdered product is able to be easily rehydrated in cold water, but resultant dispersions are not equivalent to freshly prepared paste due to starch degradation. These pre-gelatinized starches are used because of water holding and thickening properties in many foods. For example, preparation of instant puddings and frozen fruit pie fillings use this pre-gelatinized starches. In preparation of instant puddings, a packaged powder is mixed with cold milk and allowed to stand for a few minutes. Then only simple pudding is prepared. This powder is a mixture of pre-gelatinized starch, sugar, flavorings, and some salts are also added to it to produce viscosity increase in the milk to keep the starch suspended until hydration can take place. Even for frozen fruit pie fillings, pre-gelatinized starch is used to keep the fruit suspended and helps retain the flavor for long time. Next modified starch includes cross-linked and other derivatized starches. A great number of esters and ethers of starch of infinite range of physicochemical properties, that is heat stability, can be prepared. But use of such derivatives in food is restricted, and only a few of these are important in the food industry. Starch phosphates. Important example of starch derivatives is suitable as food additives, and it is used for preparation of many food products. Introduction of free acid groups. To prepare starch phosphate, both introduction of free acid groups into starch phosphates both increases and stabilizes the paste viscosity by the negatively charged phosphate groups, expand the molecule in solution, Coulombic repulsion, and prevent the formation of aggregates. Because of high viscosity and paste clarity, starch phosphates have been used extensively in foods as thickeners and texturizing agents. Their resistance to molecular aggregation is important in formulation of frozen foods. Swelling and ultimate breakdown of starch granules during cooking can be controlled by introducing a suitable number of cross linkages between the molecules by esterification with trimetaphosphate. Starch with low level of phosphate cross-linking is also used in textural modification of food. For example, cross-bonded phosphate starches are used as thickeners in salad cream and fruit pie fillings. Introduction of hydroxyalkyl substituent increases the solubility of starch and prevents molecular aggregation. For example, hydroxypropyl starch. Hydroxyalkyl starches gelatinize at low temperature than the parent starch and paste show little tendency to form gels. Cellulose, very important polysaccharide, is most abundant polysaccharide in nature, acts as main structural material in plants. This is linear polymer of D-glucose units linked by beta-1,4 linkage. It is unbranched polysaccharide which contains as many as 5,000 glucose units. Because of the beta linkage, glucose units in the chain alternate. Molecule is effectively rigid and straight chain because of this alternating character of glucose in that cellulose chain. Cellulose molecules readily align themselves side by side in an arrangement which is stabilized by intermolecular hydrogen bonding and form crystalline regions, which is insoluble in water. Cellulose is responsible for form and gross texture of the foodstuffs. Being insoluble, it is little affected by cooking process and does not disperse. On ingestion, even it is not digested because there is absence of cellulose enzyme in human being, so it is not digested and does not hydrate. This is structure of cellulose. Here you can see beta-1,4 linkages between glucose units. Now glycogen. This is reserved polysaccharides exclusively found in animal body, in muscles as well as liver. It resembles starch in its chemical properties and formed by condensation of a large number ranging from 5,000 to 10,000 of glucose molecules. It is a branched chain polysaccharide resembling amylopectin. Its chain length is of 8 to 10 glucose units, and molecular weight of glycogen varies from 105 to 108 daltons. Hemicellulose. This is also one of the important polysaccharides, also known as dietary fiber. It is present in many plant tissues. Structural components of the cell wall. It is water-soluble, non-starchy polysaccharides. It is heteropolysaccharides. Monosaccharide units present are xylose, arabinose, galactose, glucose, and glucuronic acid. It is non-fibrous, where cellulose are fibrous polysaccharides. It is more soluble in alkali and more readily hydrolyzed by dilute acids than cellulose. Pectins. Pectins are also important polysaccharides. Specifically, this is very important for preparation of jelly and marmalade in food industries. This is found in primary cell walls and intercellular layers in the plant and most abundant in young tissues. This is characteristic constituent of fruits, specifically citrus fruits, may contain up to 30% of the pectin. Pectin family of closely associated polysaccharides, which is difficult to separate. The term pectin is used in relation to water-insoluble polysaccharides. D-galacturonic acid, its principal constituent, is esterified as methyl ester and possesses considerable gelling power. Other constituents of pectin may include D-galactose, L-arabinose, D-xylose, L-rhamnose, and L-fucose. Three types of homopolysaccharides also are present, including D-galacturonan, D-galactan, and L-arabinan. Pectin is typical heteropolysaccharides associated with pectic substances include the soybean L-arabino D-galactan. This is divided into two classes, that is high methoxyl pectins and low methoxyl pectins. In high methoxyl pectins, more than half of the carboxyl groups are in the methyl ester form, whereas in case of low methoxyl pectins, less than half of the carboxyl groups are in the methyl ester form. And these low methoxyl pectins are widely used for preparation of marmalade and jelly preparation. High methoxyl pectin solutions gel in the presence of sufficient acid and sugar, whereas low methoxyl pectin solutions gel only in the presence of calcium ions, which provide cross bridges. Here in this structure of pectin, you can see esterified D-galacturonic acid resides in an alpha 1,4 chain. The acid groups along the chain are largely esterified with methoxy groups. Here, with methoxy groups in natural product. So this is structure of pectin. That's all about polysaccharides. Thank you. Thank you very much.